Hello all, welcome to another video with me, Varun on Tech Tablet. In this video, we'll be talking about the first part of fourth unit, which talks about the applications and case studies in data science. And while we are discussing this topic, let us understand what all things we have important and what all are the things that we need to cover from an exam perspective and also for generic understanding of the unit. Now, this is with the accordance of AKNU syllabus. And as I said, we are covering unit 4.1. So this would be the agenda of today's session. Now, going forward, what would we cover today in unit 4? So the first part would be to understand simple linear regression. Again, it's not as simple as it sounds, okay? The second one would be to talk about multiple linear regression. The third one would be to talk about the model evaluation, which is accuracy, confusion matrix, ROC. There are too many other factors or too many other points that we need to understand. But yes, we'll be talking about the matrix in today's class. So the first things first. Here, let us understand what is simple, linear, and regression. Now, before we get deeper into the subject, let us understand the words first. Because if you've understood the words, then I think it becomes very easy for you to understand the subject itself. Simple needs no understanding. It is 1:1. Okay, so you have one dependent variable and one independent variable. Now, what do we mean by the word linear? Now, a lot of times when I ask a lot of students what is linear, people say that it's a straight line which goes on and on. It's a straight line with 2 points. It's a straight line which does not have any points. It's a line which goes in circles. I have all weird answers, but I think the answer to this is very simple. Linearity basically discusses about the relationship of two variables. So here you have x-axis, right? This is your x-axis and this is your y-axis. So here we are trying to ask the system what is the relation between x-axis and y-axis and how are they dependent on each other. So linearity talks about the relation between x and y. Okay, relation between x and y. While regression talks about the kind of relation. So is it positively related or is it negatively related or is it neutral or is there no relation or things like that. Now, how does simple linear regression work out in real parlance or in real world? Must be a very big question. So what happens is here, as discussed, we have one input and one output that we work on, right? Now, in this one input and one output, the x variable or the x-axis is called as the independent variable, while the one on the y is called dependent variable, right? Now, what is the difference between independent and dependent? Now, let us consider two examples, two very basic examples. Okay. One, is the health dependent on smoking or is smoking dependent on health? Well, it is very straight and very clear that your health becomes dependent, right? And smoking becomes independent because based on how many you smoke, we can try to calculate how deep is the damage of your health. Simple, right? Likewise, here you have another example that is hours studied and exam score. So based on how many hours you've studied, the exam score varies. So here it is very easy to say that X, which is hours studied, is independent and Y, which is exam score, is dependent, right? Now we try to apply these independent and dependent values in the equation of the line. Okay, so here you can see you have a small equation of the line, while this is also written as y is equal to mx plus c. I mean, this is more famous, though the one here and the one here are the same. There's no difference between them. Both of them, I mean, just the notation is different, but there and here, in both the places, we are just trying to calculate the same damn thing. Okay. So what are the variables that we have here? You have m, okay, m, which is here. You have x and you have c. So now let us understand each of these, right? So here c becomes your error. All right. Then you have M and X, right? So now what are these? Let us try to understand these. So here M becomes the slope. Okay. And X, X1, X2, X3, these are the points. Now, how do we implement them? Like, what is the coding way of doing it? So here you have LM, which talks about the linear model. In our language, you can directly use this, code. And here I'm trying to check the score based on R. So score is the independent and R's is dependent. And obviously, you'll have to give the source of your data as well. So the data is some student's file and it's getting into the model. And the line, now whenever you're working on these, a line is chosen to minimize the total squared distance between actual and predicted. Now, what is actual and predicted? You might have a question like this. So now, based on A, B, C values, I want to see how is a person studying, okay? So here, these are points that you see, like 1, 2, 3, 4, all these data points. These are the actual data points. Like these are the data points from the data set directly. Now here you see another line which is completely smooth, right? Okay, it's a smoothened line. It's not a proper line. Okay. Now when you look at this line, right, you are seeing that there is a difference between the actual point, right, and the predicted point, which is this. Now this difference becomes the error. Okay, now I'll just write it here for you to understand. Now this error has to be as low as possible in a good linear regression model, right? So in least squares method, a line is chosen which minimizes the total squared distance between the actual and the predicted. Now, why do we do this? Because lower the error, better the model. It's as simple as that. Now, there is also something called as multiple linear regression. In simple linear regression, you have 1:1 cardinality. That is, you have one dependent variable and one independent variable. But when we talk of multiple linear regression, right? Multiple linear regression has multiple input points that you can take, right? So here, as you can see, we have a small, line written here. You can see house price. For example, hours of study may be the only factor for a person to score well. But when we are talking of multiple linear regression, here you have multiple values. It's not just one single value. Like house prices are dependent not just on the area, they are dependent on the size of the house, number of bedrooms, location, age. They all play a different role and a very important role as well. Now, in cases like these, where you can't ignore one or you cannot just consider one value, this is where multiple linear regression comes into play, right? Where one variable isn't just enough, right? Now, having said this, you have multiple inputs or many inputs, but the output is only one, right? So how does house price, okay, which is house price is dependent on size. House price is dependent on location. House price is dependent on age. So it would be right to say that house price, which is an independent value, is dependent on multiple dependent values, right? Like size, bedroom, age, location, etc. Now there's a formula that we follow here as well. Again, it's y is equal to mx plus c only, but y is equal to, you have first m plus m1x1 plus m2x2 plus m3x3 plus c. So that's how it goes, wherein the value of m is how does x change with respect to y. So when x is increased by 1 unit, how much does y change? Okay, now this is what we try to find out here. Then we have another value which is called adjusted R square. Now, adjusted R squared is a very important value that we use in multiple linear regression. Now, what happens here? In adjusted R squared, as you can see, a heavier value or a higher value is penalized. Now, why is it penalized? It is penalized because you want the model to fit better, right? So whenever there is one value which is exceeding, and this is the generic value range, now this value from here to here that you see, it would be penalized. And because of this, we would be able to achieve a higher adjusted R squared. Now, R squared is a score, okay, and this score is generally close to 1. Okay, the closer to 1, the better the model. Okay, so that is the understanding of R squared. And adjusted R squared or a higher adjusted R squared value you have, better the model fits without overfitting. Simple. Okay, and just to give you all a small example, a real-time example. So here you can see, I'm trying to predict the house rent with the size of the house, the price of the house, the age of the house, etc. Okay, so all these are pretty much possible using basic machine learning models. Now, how does the model find the best value? Like, how is it possible? Now, there are so here, let me draw a small graph for you. Okay, so this is a graph. Here I have multiple, data points on the graph. Now, 1, 2, 3, 4, 5. So as you can see, I have drawn 5 lines. 1, 2, 3, 4, 5. Now, of all these lines, which is best? How do we know that? This is exactly why you have the OLS method, which is the ordinary least squares method. Now, what happens in this method? There are infinitely n number of lines that you could draw through a scatter plot, just like how we did here, right? Now, when you can draw n number of lines, then you need to pick up one which shows you the minimal predicted error, right? That is exactly the job of OLS. OLS, which is ordinary least squares method, it picks one line wherein the error produced is minimal. Now, this is the most important thing that you need to know, right? So, we have another variable also, or we have another, metric that is calculated. Now, how does it work? We'll look at it later, but right now let us understand OLS a bit better. So you draw a line. Okay, now when you draw lines, let us say this is how your output looks like. You have 1, 2, 3, 4, 5, and this is the line. Now, these dots, which is actual, and this line, which is predicted, the difference is calculated between them. Once the difference is calculated, I mean, this difference is called residual. Okay, and that's exactly what we're trying to explain here. See, let us start with a candidate line. For each data point, you measure the vertical gap between the actual value and the predicted value. So this is the actual value here on the system, and this is the predicted value. So there is some difference between actual and predicted. Now, this difference is called residual. That's what we were talking here, residual. Okay. Now, when this residual is available, or when we know that this residual is there, sometimes it might be positive, sometimes it might be negative, sometimes the errors might be way too large, right? Now, in this case, large errors are penalized, on a higher rate. It's like, why do higher, salary bracket people pay a higher tax? It's just that, people with higher salary are penalized more. In very similar ways, people with higher or, the data points with higher residuals are penalized more. There's no deeper understanding than this. Now, the goal is to minimize the total. So what does OLS do? OLS finds the exact M0, M1 or beta naught and beta 1 values that make the sum of all squared as small as possible. And this line is called the best fit line. So how is the best fit line generated? Through OLS method. Next time, when someone asks you, now you know what to answer. Okay. Now here you can see there's a small, deeper understanding for us if it might help you. Think of each data point as a nail on the wall, and regression line as the rubber band stretched to minimize the total pull from all the nails equally. So now you have randomly, hit some nails on the wall at different points, and you are using a rubber band that will go through all of the data points as equally as possible. Okay, so this is what happens in OLS. So now there are a few assumptions that you have to follow whenever you're working on linear regression, and it's a mandate. The first one is linearity. Now, what is linearity? There should be a straight line, or there should be a line, when you use a scatter plot. that shows a trend, and you're not supposed to find a curve. It's supposed to be a line. The second one is independence. Each observation must be independent of each other, else there's a problem. Okay, so this is the first, linearity. The second one is independence. The third one is homoscedasticity. And the fourth one is normality of residuals. Now, what do we mean by homoscedasticity? The residuals that you see, what is the residual? It is actual minus predicted. The residuals that we see, they should have constant variance. If not, the error increases. And then finally, normality of error. To check this normality of error or normality of residuals, there is something called as a QQ plot, a quartile plot. And this plot is very commonly used in our language. It is used to check the residuals, the normality of residuals. Now, there's another important thing for you to know, that is, whenever you are working on a plot like in R and you want to generate it on a model, you have 4 diagnostic plots that come up by default. The first one is residual versus fitted, that is actual versus predicted. You have a QQ plot, quartile plot, you have a scale location, and finally Cook's distance. Okay, now why do we need all these? Like, would any of these help us do anything good? Yes, these reveal the assumption violations instantly, which means if your linear regression is being used and there is a problem, then this is the graph, or these are the graphs that will help you have a deeper understanding as to how good your model is. Now, every algorithm comes with a danger, and the name of the danger of this specific algorithm is multicollinearity. Now, what do we mean by multicollinearity? Okay. Now, when two variables are completely correlated to each other, okay, or when I say completely, I mean highly correlated to each other, the model cannot, predict which of these is causing the effect. And this becomes the problem. Now, why does it have to know which of these is causing the effect? Because sometimes, now let us say you have a health problem and there are A, B, C, D, E, and one of them is very dangerous, like smoking. You swim, you play, you smoke, you sleep, and you eat. Of all these, how would I know if it is swimming which is causing the problem or if it is smoking? Right? There's no chance that I would know as a doctor just by looking at a patient. Now, we all know that smoking is dangerous, but notwithstanding that, how would I come to a conclusion? Now, this is where multicollinearity becomes very dangerous. Now, why is it dangerous? Because coefficients become unstable and they become very hard to interpret. And because of this, standard errors inflate. You see how basic errors become bigger. Now, how do we fix this? How do you find, collinearity, if it exists or not, and how do you fix it? There is something called as VIF. VIF stands for variable inflation factor. Variable. Okay, let me just rub this. Looks a bit odd. I'll just cut this here and I'll write it inflation. Okay, I tried to delete it. I think there is some problem with the eraser. Anyways, so here we have variable inflation factor. Now, what does variable inflation factor do? It basically checks if there is a very serious relation between variables or if there is not. Nothing beyond this. If the variance inflation factor variable, okay, it's not a variable, it's a variance. Okay. This is also a mistake. If the variance inflation factor is more than 5, it's a problem. But if it is much more than 5, then I think you cannot work on the algorithm anymore. You need to fix the algorithm first, and only then you can go further. Now, here you have a real-time problem. Let us just try to understand what it says. You're trying to predict car fuel efficiency using both engine size and horsepower. Now, both of them are correlated. Now, how would you understand which of these is laying a higher effect? Now, that happens through VIF, that is variance inflation factor. Do check out what is variance inflation factor when you get time. would be a really big help for yourself. Then we have, okay, I think it's time for us to delete. Okay, so now we can happily go to the next one. Right. So here you have the confusion matrix. Now, what is a confusion matrix? Confusion matrix is basically, again, ideally we have different, error findings for a linear model. You have RMSE, you have MSE, you have MAE, that is root mean squared error, mean absolute error. But right now we are looking at a confusion matrix only. Now, what does a confusion matrix do? A confusion matrix gives us the values of how good a model is, and it tries to break the prediction into four categories. And it's not just right or wrong, it also talks about how it was wrong, right? Here you can see we don't just understand if it is right or wrong, we try to understand how it was wrong. Okay, so to this you have four values: true positive, false negative, false positive, true negative. Okay, like TP, TN. You have Fn and you have Fp. Simple, you can remember it like this. Like trues go diagonal and false go diagonal, right? Now, what do each of these do? You might have a question, right? Now, let us say we have a cancer patient who goes to a hospital to diagnose himself if he has cancer or not. This is where things get a bit, serious. So the person says yes, and it was a yes. So there's no problem. I mean, all good. The person has cancer. He was detected with cancer. So that's good. Now let us understand a second. The person says he didn't have cancer and he was not detected with cancer. So correctly cleared, the test, which is case 2. Then you have false positive, which means the person has cancer, but he was detected with no cancer. Now, this is called a type 1 error. Please remember, all or both the false values, that is false positive, is called type 1, and false negative is called type 2, right? Now, type 1 error and type 2 error, both of them are the ones that you need to avoid, okay? Which means here you have, mark the person who does not have cancer with cancer in T1, which is dangerous. And in T2, the person does not have cancer, but you're declaring him as cancerous, okay? So it is also case of a mistake. Now, please remember, if you're working on data science, then the context of importance changes in every domain. Like, for example, if you're in a medical diagnosis, false negative is more dangerous. If you are in IT, then probably false positive is more dangerous. So it depends on the context and where you're working and what you need to do out of it to be able to give your right answer. Then you have precision, recall, and F1 score. What are these? Precision, recall, and F1 score. Sometimes just accuracy is not enough. Okay, you need more values than accuracy. Now, that is where you have precision, recall, and F1 score. Now, what does precision do? Okay, precision talks about, of all the values that I have predicted as positive, how many are actually positive. Okay, like how many values have been predicted and how many values of positive are correct. Okay, then you have recall. Recall talks about, of all the actual positives, how many did I correctly identify? Okay. Then you have third one, which is F1 score. F1 score is generally used when you are working on a single balanced metric. You don't want too many values. You just want one single balanced metric. Now that is the time when you use F1 score, right? So you have precision, you have recall, you have F1 score. Precision is used probably in a domain where FP gets costly, that is false positive. Recall is more active when Fn gets dangerous, that is false negative. Okay, so these are the two things that you need to remember. Now, no matter whatever model you're working on, generally, how do you work on it? So the first, thing that you do is to, I mean, even before you split your data, you understand your problem statement, right? You understand your problem statement. Okay, once you understand, then you work on EDA, which is exploratory data analysis. Then you clean, transform, manipulate. All this is done. You clean your data, transform your data, manipulate your data, and then you go into splitting your data next. Now, what do you mean by splitting your data? The whole data is split into test and train case. Test usually has less, train usually has a lot. Okay. Now, once you split your data and then you train your data, now what happens when you train the data or when you train the model? Here, your values are getting, taken in, they are being understood, the pattern is being recognized, and based on this, in the next step, prediction happens on the test set. So it's like you're training the model and then you're giving it a new paper to check if it is actually working or not, right? Now, how good is it working? You don't know. Now, to do that, you have these are called evaluation metrics. Now, what is evaluation metric used for? Okay, so here you have things like RMSE, root mean squared error, MSE, mean squared error, MAE, mean absolute error. You have accuracy, you have precision, recall, F1 score, R1, etc. So all these, they all are evaluation matrix only. You do not have to check only for confusion matrix. Please remember, confusion matrix as specified here is used for classifiers. Now, this is how your syllabus is designed. So I had to follow that. But otherwise, we do not use confusion matrix for a mathematical numerical model. It's moreover used for classification model. Then once you have your error matrix that is generated and now you know how good your model is performing, what, why, and when, then you go on to plot the ROC model. Now, what is ROC? It is receiver operating curve. Okay, now what does this do? ROC basically calculates AUC. Now, what is AUC? AUC is area under the curve. Okay. Now, higher the AUC, better is the model for you to implement it. Okay. So yeah, that's about how you work on a model and how you implement it. Then you have ROC curve, receiver operator curve. It talks about how a model is, performing, right? It shows the trade-off visually. Okay, now what do we mean by trade-off? Here, let's take a small example that we have at the top. Imagine adjusting how strict your spam filter is. Okay, at low threshold, it catches all spam, but also blocks real emails. At high threshold, it misses spam. Now, how do you balance between the right, you don't want it to be minimum, neither do you want it to be maximum. You want it to be optimum. In this case, an ROC gives us the right value to understand it. Now, what does ROC plot? ROC plots on the x-axis, it has false positive rate. On the y-axis, it has true positive rate. Okay. So, both of them are positive only. One is false positive, one is true positive. And with the help of this, we generate an AUC, that is area under the curve. If the area under the curve is 1, then it's a model which is too good, which is close to impossible. If it is 0.5, then it's okayish. But if it's 0.8 or above, then I think it's a really good model. Okay. So this is what we have in model evaluation, which is the last topic of 4.1. So in the next topic, we'll be looking at some more machine learning that we have. Okay. This we would be learning in unit 4 only, but the video would be 4.2. Do check out for any queries or any questions or any career related suggestions, or you want to have a word with me regarding what you want to do next. You could reach out to me on my email ID, or you have a comment section right below the tab. All right. So thank you very much. Without any further ado, I would, wish you all a bye-bye. See you all very soon. You all have a great day ahead.